Last time we saw how to install, how to set up a clone node for Bitcoin Core. We saw how to create watch-only full wallets, how to import descriptors, how to export them, how to look at the xpubs and the xprives, yeah, and such. So today I want us to demystify transactions as per the book Mastering Bitcoin. As per the book Mastering Bitcoin, yeah, yeah, this book over here. Yeah, so what are transactions in the first place? So in Bitcoin, you can just view transactions like maybe an update of the UTXO set by the full nodes. So when you make a transaction, it's like you're telling the full nodes that delete this sender and then add this recipient. Let's say, for instance, Alice is sending some Bitcoins to Bob. So you want to remove the UTXOs belonging to Alice that were used in the process, and you want to add UTXOs that were sent to Bob. Yeah, so that is what this statement means. So there's no physical cash being exchanged, it is just a record, so the value is being implied. Yeah, now this is a sample serialized Bitcoin transaction. So the author is using get raw transaction, but we cannot be able to use it because we are using a prune node. So for our case, we'll just get transaction. Yeah, so we'll just query our own transaction that we have created. So first things first, so I just want to create a wallet and then generate an address and then go to the faucets and then send some few bitcoins. Just remember that after using them, you can return them back using the address that has been offered over there. So we'll create a wallet for now. We'll create a wallet using this command. So we are using named parameters, as you can see, with the name flag. And then the wallet name, I think I will call it, let me just call it with a shorter name. I will just call it full. I'll just call it full. Descriptors has been set to true. So it will create the wallet and then it will load the wallet for us, as you can see. So it has created the wallet full and then it has loaded it. So this is the wallet creation, this is the loaded wallet. So right now we'll just generate an address. So if you want to view the descriptors, you can just look at the descriptors. So for us, we are just interested in xpub. For security reasons, it is not recommended to maybe display the xprives, yeah, for some reasons. So Bitcoin CLI list descriptors, and then I'll just put it in a file descriptors, descriptors.txt. So now here are the descriptors. So we'll just look at the transaction for, this is the legacy one, PKH, pay to pub key hash. And then this is the wrapped one, witness pay to pub key hash. And then this one is now the taproot. So they all have different structure. So some of them have different structures. Yeah, so we will just look at them. Yeah, so we have set up the wallet. So let us now just generate an address. To receive the faucet, I tried using a legacy address, but I think it is not recognizing the legacy one. I think maybe because of the old structure, which makes the transactions very expensive. So I will just create this one over here, the SegWit one, the native SegWit. Yeah, so I will call it, yeah, I'll just call it SegWit and then click enter. So now this is the address that we've created. So this is the native SegWit, and then I'll just paste it over there because we will use it. So let me now go and get some coins from here. So I'll try and get some Okay, so it has been placed, so I think we'll just wait for it. I will just try and get transactions, get transaction, Bitcoin CLI, get balance. I'll just use this one. Yeah, but the RPC wallet is full because we changed it. So I'll try and get the balance. The balance is still 0.00, so I think I will just pause it there and then come back after the process is done. So it was unconfirmed for some time, but now I can see my balance 0.004, yeah, this value over here. So right now I will generate to just mimic the legacy transaction. I'll just generate two more legacy addresses. So I will just show you the options that we have. So we have 4 options in Bitcoin Core. We can either generate a legacy address and the wrapped SegWit, yeah, the native SegWit, and then the taproot. Yeah, so these are the options that we have. So right now I'll just generate a legacy one so that we can mimic the transaction that is on the text. So I'll just call it legacy one. This is the label, legacy one, and then put legacy. So I'll just do this twice. Yeah, this one it will be legacy 2. So we have the 2 addresses right now. So all of these are legacy addresses. Yeah, so this is legacy 1. And this is legacy 2. Okay, so right now the amount that we have it in the SegWit. We have it in this SegWit. So now we just want to send some amount to these legacy addresses so that they can communicate with each other, so that we can get the transaction as it is over here. So this is the transaction that we want to mimic. Yeah, so that we can now go straight and explain the structure, how this structure comes in play. So now I will send to address. I'll just use Bitcoin CLI. Let me just copy paste these commands. Send to, okay, I don't have send to. So Bitcoin CLI, send to address. Yeah, it takes, I think I can just look at the help of the arguments that it takes. So it takes some arguments. Send to address, the first one is the address, the second one is the amount. Okay, let me just do it manually. So in this tutorial, I'll just use a single wallet. Yeah, for because it's easier. And then I want to send to this address over here. I want to send to this address. And I want to send 0.000. I think it is 40 and then 2. Yeah. So now this is the transaction address, copy transaction ID, sorry. This is the transaction ID of, this is now SegWit. to legacy. So this is the transaction of SegWit to legacy. Yeah, so we will reference it, but now we just want to send, because we send to this address ending with a 3k. So now this address has some cash, so I can just get the, I can just list the unspent. I can just list the unspent and then see our RPC wallet is called full. Okay, so for now the list unspent, there's no list unspent because the transaction has not yet been confirmed. So if the transaction has not yet been confirmed, so yeah, I can just get the balance. And now we can see our entire balance. It means that this is now our balance, because the rest, we are using the same wallet, remember, so the rest is the fee. So because we are transferring coins from one address to the other in the same wallet, so it's just showing the entire. So right now, to mimic that transaction, we'll be sending from this address to this legacy, from this legacy address to this legacy address. Yeah, so we'll just use the same send to address, but right now we'll be sending to this address over here. Copy. Now we'll be sending to this address. Yeah, so I think it takes it as a string. So I'll just send yeah, this value, so that, so now this is the legacy to legacy copy. This is now the legacy to legacy TXID of legacy to legacy. Yeah. So now we have both transactions. So now we can just come back to the tutorial and see. So for us, instead of get row transaction, we just get transaction. Yeah, we'll just use get transaction. Okay, get transaction. Okay, so I'll just use Bitcoin CLI, get transaction. Let me first get help. Yeah, so this is the transaction, so it's just this. Yeah, but now instead we will look at, first of all, the legacy to legacy transaction. We first look at the legacy to legacy and use that transaction ID. Yeah, so now this is the transaction, how it looks like. So now what is being displayed over here is this value over here. This is the value that is being shown over here. So maybe we can just copy it and then maybe paste it over here. Now this is the value. As you can see. Yeah. Now this is the value. You can see. Now for the differences that come, this is now the only difference I think that comes, because for the legacy transaction they were version 1. Yeah, but nowadays the transactions are version 2. Yeah, because of the sequence, because of the log time. Yeah, and the the sniping attack that miners had. So that is why it looks this is version 2. So as you can see, this is the first byte, the second byte, the third byte, and the fourth byte. Yeah, so this is now version 2. That is the only difference between this transaction and this transaction, because this is version 1 transaction. Yeah, but basically it's legacy, as we can see, as we will see. So now we'll just go to the map, to the mapping, and see the different components of a transaction in real time. So the first one is the version. The first 4 bytes of a serialized Bitcoin transaction are its version. So the original version of Bitcoin transaction was version 1. Yeah, this was it. All transaction in Bitcoin must follow the rules of version 1 transaction. So there's this version 2 transaction that we can also see in our own transaction. As you can see, this is a version 2 transaction. They were introduced with BIP68, so this was the relative time lock. Yeah, so they were introduced because of the end sequence. Yeah, that was there. So yeah, so I think that is what deals with the version. So what you should just understand with the version is that the version is the 4 bytes of the transaction. So when we come to a transaction, and you come to the hex part, you can see the first 4 bytes that tells that this one is a transaction that was it is a legacy transaction, but nowadays the version has become the default one. The version 2 has become the default one because of the changes that have occurred, as you can see. So this is a legacy to legacy, but it is version 2 instead of version 1. So we'll now go to the other components of a transaction. So there's the extended marker and the flag. There's the extended marker and the flag. So it says that the next 2 fields of the example serialized transaction were added as part of the segregated witness soft fork change in Bitcoin consensus rules. So the rules were changed for BIPs 141 and 143. So for our case, we don't have the marker and we don't have the flag field. As you see, let me just go back to our transaction again. So the next 2 fields should be the marker and the flag. For our case, there's no marker, there's no flag. There's just this that shows the number of inputs in our case, as the author is explaining over here. In legacy serialization, the marker byte will not have been interpreted as the number of inputs. 0. A transaction can't have 0 inputs. Okay, so if the transaction doesn't need a witness tag, the marker and flag must not be present. So the marker and the flag are not present over here. So it is replaced by just this, yeah, which shows the number of inputs that our transaction has. Okay, so because this is not a witness transaction, so let me just give you an example with a witness transaction. A transaction with a witness. So I'll just use the same, but now I'll just take this one. So this one must have a witness because it's the transaction that we've sent from our SegWit to legacy address. So I'll just go through it and see. So I will just take this hex over here and paste it again on our console. So I'll just paste it again on our console. Okay, so this quotes. So I've pasted it again. So this is the first byte, the second, the third, and the fourth. So these 4 bytes are still for the version. So it shows that this is also a version 2 transaction. But now there are 2 added fields, this one and this one. As you can see from here, it says if the transaction includes a witness structure, which we'll describe in witness structure, the marker must be 0. As you can see, the marker is 0. And the flag must be non-zero. Of course. So now in our case, the flag should always be 1, which is 1 for our case. Yeah, so as you can see now, you can tell the difference between the legacy one. For the legacy one, there was no witness structure. That is why, even though it was version 2, but it had no the extended marker and the flag field. What was there was just the number of inputs, which we can see over here. Yeah, so that is as much as version is concerned. So the version was changed to 2 because of the use of end sequence, and maybe yeah, and the relative time lock. Yeah, so this extended and the marker field came with the witness structure. Yeah, so in our legacy there's not. So so far we've seen at the version and the extended marker and the flag field. So now we are going to the inputs. So the input field contains several other fields. So let's start by showing a map of those bytes. So let me just close this. It is so now this is it. So there's the count, there's the previous output transaction ID, there's the previous output index, there's the length, and there's the sequence. So the first one, so now we are in the input. We are in the inputs. So the first one is the length of transaction input list. Okay, so we'll just get a broader view of it. We'll just go in depth. Going in depth, so we'll just put the true over here so that we can see all the information that we require. So this now this is the input. This is the input. So for the transaction, we saw the transaction. This was the transaction. Yeah, so we saw this the version, and we'll also see this size, the weight, and what. But we've seen the transaction. We've seen the extended. We've seen the flag. So now we're in the inputs. So this is the input field. It says that the first one is the length of transaction input list. Okay, there's no point of just putting the length because we can find it easily. It's an array. It's an array. So this input is just an array of objects. So it is not hard to find. So we can just come over here and just use it as it is. Yeah, so I think it is normally derived. I think it is normally a calculated field because it is very easy to calculate it because this is just one, as you can see. So even though it is shown that it is there, it is not explicitly defined in the transaction inputs, as we can see. So the object, the first one is so it should be somewhere, I think. Yeah, but it is not there, so I think it can just be gotten very easily. So that is the first one, the length of transaction input list. Okay. Okay. Yeah. So the second one is the out point. So a Bitcoin transaction is a request for full nodes to update their database of coin ownership information. So this out point just shows the previous transaction ID that the sender received the coin so that they can send now to the next recipient. As you can see over here. Yeah, so this is now our out point. Yeah, and you can just identify the out point by the transaction ID and the value of the output index. That is these two over here. So that is the out point. A Bitcoin transaction is a request for full nodes. Okay. The output contains a 32 bytes transaction ID of the transaction where Alice received the bitcoins she now wants to spend. This transaction ID is in Bitcoin's internal byte. Okay, so this is now the transaction ID. So now when we query this one, we will determine if it is spent or unspent and from where they receive this Bitcoin that they now want to spend. And it also, yeah, so because transaction may contain multiple outputs, Alice also needs to identify which particular output from that transaction to use, call its output index. Output indexes are 4 bytes unsigned integers starting from 0. So now this is the output index that they want to spend, because a transaction might have several outputs, so you must know the exact one to spend. Yeah, so now this is that value. Yeah, that is that value. So upon finding the previous output, the full node obtains several critical pieces of information for it. The amount of bitcoins assigned to that previous output, the authorization condition for that previous output. Yeah, so these are just some of the things. So it is very easy. So assuming we are a full node, it is very easy to just come over here and look at that transaction. But for our case, we will not find it per se, because we are using a prune node, and this was the transaction from the faucet. So if we want to find the previous transaction, we can just query the transactions that we have sent. I think that was the second transaction. Yeah, this transaction over here. And I can come here and just say false and the true flag. Yeah, for the verbose. So because I want to get the verbose information, when I come over here, I'll see. So this is the transaction ID, and you can see it is the same. It is the same because the pathway that we used, we got the finances from the faucet, and we used this address to get the finances, the coins, and then after getting the coins, we send them to this one. We got this transaction. So this transaction is now the out point. Okay, so this transaction is now the out point. So now when we query this transaction, we'll be able to get this information: the amount of bitcoins assigned to that previous output, the authorization conditions, and the height of the block of that, and prove that the previous output exists in the blockchain. That means that it exists in the UTXO set. Okay, it is not spent already. Okay, so this just tells us how to track it, and maybe some explanation. Yeah, some explanation. So the other field, so this is the field for the out point. I think, yeah, this was the out point. So we've understood the out point. The out point is just the previous transaction of this one. And by getting this previous transaction that we can see is similar to this one, by getting that previous transaction, we can now get the everything that we need to know about that transaction, and if those coins are indeed spendable. After the out point, now we are going to the input script. Okay, so the input script field is a remnant of the legacy transaction format. Okay, so it's a legacy remnant. Okay, so in the legacy transactions, they are there, but in the current transaction, that is the wrap SegWit and the native SegWit, it is not available. So the length prefix in indicating the length of the, in this case it's a single. Okay, so for our case, I think we can just come here and look. So when you see that the script sig is available, as you can see, the script sig is just made up of the public key and the signature. So because this is a legacy transaction, we were transferring from legacy to legacy, it means that the script sig has been populated. Okay, when we go to the other transaction, this transaction over here, we will notice that the script sig is empty. The script sig is empty. Yeah, because the information was transferred to the transaction witness. So here is where the signatures are. Yeah, so as we can see, so this is just a short description of the input script, and then there's the sequence. The final 4 bytes of an input are its sequence number. The use and meaning of this field has changed over time. Okay, so in the past, the sequence was being used to create multiple transactions without really broadcasting them. So it has been transferred to, I think it is being used by the Lightning Network and the channels. Yeah, so right now the sequence has some changes that are being explained over here. So it is used for replace by fee, and it is also used for relative time locks, as you can see. So this field over here, this is the sequence. Let me just look at it. This is the sequence, as you can see. So it has changed over time. Right now it's being used for RBF and the relative time lock, but in the past it was being used to create multiple transactions without necessarily broadcasting them. Yeah, that is now incorporated in most Lightning Network applications. So I think that's it. That's it for the inputs. That's it for the inputs. So as you can see, we saw the inputs. Let me go again. We saw the version. We saw the inputs, the input length, which can be calculated as the length of the array. We saw the out point, and because there are multiple outputs, there can be multiple outputs in a transaction. We normally get the transaction ID and the index of that specific output. We saw the script sig, and we identified that the script sig is empty for newer SegWit transaction, that is wrap SegWit and the native SegWit, but it is populated for the legacy transaction. Yeah, so for this newer transaction, there's this transaction witness over here, which is not available in the legacy one, as you can see. So in this legacy one, the script sig is populated, and there's no witness. In the other one, there's witness. And then we also saw the sequence, whose function has changed over time. It was being used for multiple transactions, but nowadays it's being used for end sequence and absolute log times. So now we are going to the structure of the outputs. So this is just a rundown. So the output field of a transaction contains several fields related to specific outputs. Just as we did with the inputs, we'll start by looking at the specific bytes. So the first one is the output count. And just as we saw in the inputs, it is not reasonable. It is reasonable, but I don't think it is urgent to put the length of the outputs, because we can just calculate it very simply. Like for this case, we can just get the number of outputs available in this array. You can just get the number of outputs. Okay, which is 2. So for this case, it is just the same thing. There's the output count, identical to the start of the input section of transaction. So it just shows the length of this array, or the length of this vector. Okay, so there's the outputs count, and then there's the amount. There's the amount. So this is the amount. So here we have 2 outputs. So this is the amount, which is the value. This is the first amount. This is the second amount. Yeah, so this is, so we'll look at the structure of one of them. So this is normally called the value. The amount is normally called the value. So the first field of a specific output is its amount, also called value in Bitcoin Core. As we see, it's an 8-byte integer, yeah, indicating the value of that output. And then here we are just getting the uneconomical outputs and disallowed dust. So this is when maybe the amount that the fee that you are using is maybe more than what you'll be getting. It doesn't make sense, so it is normally counted as dust, because it is I think it's just loss. Okay, and then after that we have the output scripts. So we have the output scripts, as you can see over here. So this is the script pub, and this is now the output script. So it is normally called the script pub. So here it is the native SegWit, and that is why you can see this string over here. I think you made something like this in the previous chapter, I hope. So you duplicate and then you hash and then and then search. So if you want to read in terms of hex, this is the hex. But now this just shows the conditions that are required for consumption of this transaction. So let us see. So in that case, the transaction ID is normally equals to the witness transaction ID, as you can see. So they are just the same. Yeah, because it is not using the witness structure. As you can see from the inputs, so the input does not contain the witness structure. It's just the script sig that is populated, unlike the other one. The other one, the script sig is empty, but the witness structure is over here before the sequence, that contains all those values. So that's it. So we just went through the descriptors. The first thing that we did was creating a wallet. We created a full wallet. With these descriptors, we use the pub key hash, which is the legacy one. We use the wrapped SegWit, which is sort of new. We use the taproot and the native SegWit. This is the native SegWit. And we saw the different types of fields. In inputs, in outputs, and in transactions. We saw the sequence, we saw the versions, we saw the witness structure. So we saw almost everything. So this was just a short description of the demystified transactions based on the Mastering Bitcoin book. So I hope it will help you to understand better. So when it comes to lock time, okay, so this lock time was just introduced. So the final field in a serialized transaction, it is its lock time. This field was part of Bitcoin's original format. Okay, the transaction indicates that it should be eligible for inclusion on any block. So let me just try and explain this lock time just a little bit. So when we see this transaction, we can see a lock time over here. So this lock time is it just represents the earliest block that this transaction should be added into. The earliest block. So this prevents the snipping, where maybe it can be added in the latter blocks, by a miner somewhere. So now what this lock time does, so it cannot be added in a lock time that is lower than this block height, that is. So that is the most important thing about lock time. So that's it. So if you have any question, so if I can just point out, so the real block height that it was added to was this one. So you can see that it is a later block than the lock time. It is a later block than the lock time. So it was added in the next block. That was 83. This one is 84. So I hope you've understood the structure. So this was just demystifying the transaction based on the book. So that's it. Thank you.